Understanding Past and Present Climate Change, Lessons from Ice Melt and Ocean Dynamics. Welcome to our deep dive into climate change dynamics. Today, we explore the significant impacts observed during the last interglacial period, marked by ice melt and rising sea levels. We'll assess how these historical events offer insights into the present and future climate scenarios, with a focus on paleolithate data and contemporary climate models. Our examination underscores the critical importance of understanding these phenomena for shaping informed climate strategies. During the last interglacial period, temperatures were less than 1 degree Celsius warmer than they are today, yet resulted in substantial ice melt and sea level rise of 5 to 9 meters. This period serves as a crucial point of reference, highlighting the sensitivity of ice sheets to even modest temperature increases. By studying these historical records, we gain valuable insights into the potential trajectory of Earth's climate system, offering a stark panorama of what might occur if current trends continue unmitigated. The magnitude of human-induced climate forcing contrasts starkly with natural historical variations. Industrial activities have introduced greenhouse gases into the atmosphere at unprecedented rates, surpassing paleolithate events in both intensity and timescale. This anthropogenic influence necessitates urgent scrutiny and robust response, as it heralds an era of climate dynamics without analogue in historical records. Ice sheets in direct contact with the ocean, particularly in Antarctica and Greenland, demonstrate heightened vulnerability to oceanic thermal increases. Research suggests that these ice sheets are susceptible to nonlinear disintegration processes, which could prompt rapid and significant ice loss. Such mechanisms have the potential to accelerate sea level rise, posing a profound threat to global coastal regions. The rate of ice sheet mass loss can be approximated through a model of doubling time, with estimates suggesting that a 10, 20, or 40-year doubling period could yield sea level rises of several meters over the next 50 to 200 years. This projection underscores the urgency of immediate and stringent climate actions to mitigate impacts and avert catastrophic outcomes. Subsurface ocean warming is a pivotal driver of ice shelf melt and consequent ice sheet discharge. This phenomenon triggers a cascade of climatic shifts, including feedback loops in the Southern Ocean that exacerbate warming conditions. Such feedbacks can drastically alter ice dynamics, necessitating comprehensive monitoring and enhanced predictive models to better grasp and respond to these complex processes. The Southern Ocean plays a critical role in modulating global climate, primarily through its impact on Antarctic bottom water production. Recent models have identified a feedback mechanism that slows this process, increasing sea temperatures proximal to ice shelf grounding lines while paradoxically cooling sea surfaces. This interaction results in increased sea ice cover, impacting ocean stratification and stability, thereby affecting broader climatic patterns. The consequent alterations in oceanic and atmospheric states result in amplified horizontal temperature gradients, which enhance eddy kinetic energy and atmospheric baroclinicity. This escalation is linked to more robust storm systems, with profound implications for understanding and predicting extreme weather events on a global scale, posing new challenges for climate modeling. The interplay between the Southern Ocean's dynamics and atmospheric CO2 levels is particularly significant, given CO2's role as a pivotal regulator of global thermal conditions. The millennial scale delay observed in deep ocean ventilation and subsequent carbon dioxide alterations underscores the complex temporal dynamics inherent in the climate system and highlights the exigency of incorporating these factors into climate forecasts. Recent observations indicate rapid ice sheet melt rates, corresponding to the lower end of the hypothesized 10 to 40-year doubling times. This trend underscores the immediacy with which ice melt could escalate, necessitating urgent policy and scientific responses to mitigate further impacts. These findings bolster the case for adopting stringent emission reduction targets to curb future warming and stave off deleterious outcomes. Reaching a global temperature increase of 2 degrees Celsius above pre-industrial levels poses significant risks, primarily due to potential ice shelf destabilization. To stabilize our climate, we must eliminate Earth's energy imbalance. This objective requires a cohesive global effort, informed by insights from paleoclimate studies, advanced modeling, and current observational data. I invite you to share your insights and feedback in the comments section below. Let's collaborate in fostering a more profound understanding of climate dynamics. Don't forget to like, subscribe, and share this video if you found it informative. Stay tuned for more in-depth analyses on climate science. Thank you for watching.